Future engineers, subscribers, viewers, and students, here is the second part of Strength of Materials 2, and in this uh, video, I'm going to present two problems for spacing of bolts, nails, and for the second part about the shear stress distribution, maybe. So problem 3, a wide flange shown carries a vertical shear force of 100 kilonewtons. So which the following gives the maximum shearing stress, the minimum shearing stress in the web, and the shear in percent carried by the web. For the maximum shearing stress, it occurs at the neutral axis. So we will compute the Q in the formula VQ over IB for shear stress and with respect to the neutral axis. So the shear stress distribution, if you can recall, and this is the minimum shear stress in the web. This is the shear stress at the junction, but in the upper part, which is now in the flange part. So for maximum shear stress, the formula is shear stress equals VQ over IB, and the moment of the maximum Q rather is 120 times 20 times quantity 10 plus 80, so 90, then plus 20 times 80 times 40, the moment of this area in the web, 20 times 80 times 40. So Qmax is equal to 280,000 mm cube. The moment of inertia is moment of inertia of big rectangle with respect to the centroidal axis minus moment of inertia of these two rectangles treated as 100 by 160 cube over 12. For the outer rectangle, the dimension is 120 by 200 cube over 12, then minus 100 times 160 cube over 12. So the moment of inertia of the section is 45.87 times 10 to the 6 mm to the 4th. So substitute into this formula, tau max is V, 100,000, Q, which is Q max 280,000 over I 45.87 times 10 to the 6. B is the width of this section at the neutral axis, 20. Solving for tau max, it is equal to 30.52 megapascals. Then for tau JW, the Q is just the Q of the flange, which is 120 times 20 times 90. We have the same formula. Then B is still 20. So tau JW equals 100,000, then 120 times 20 times 90 over I 45.87 times 10 to the 6. B is 20. Solving for that, it is 23.54 megapascals. And finally, the shear in percent carried by the web. The shear force carried by the web, vertical shear, is average shear stress in the web then times the web area. So let's set up that. And remember, the average shear stress is equal to tau JW plus 2/3 of quantity tau max minus tau JW. We already computed tau max and tau JW, so we can compute tau average. It is equal to tau JW 23.54 plus 2/3 of quantity 30.52 minus 23.54, and that is equal to 28.19 megapascals. So having known this, we multiply it by the area of the web. That's the shear force carried by the web alone. So shear carried by the web is equal to 28.19. The shear area is 20 times 160. And the shear carried by the web is 9208 newtons. This is the reason why in steel design, the shear force carried by the web is equal to allowable shear stress times the area, which is equal to thickness of the web times depth. So I hope that you notice that in your subject steel design, the shear area is thickness of the web times the overall depth, because this is almost 100% of the shear carried by the section. So that's why in steel design, the shear carried by the flanges may be neglected, because this is almost the same as if we substitute D instead, not the web. We include this vertical shear, this shear area here. It is almost 100,000. So the percentage of the shear carried by the web is 100% times 90,208 over 100,000, the total shear. So it is equal to 90.21%. For problem 4, the box beam has an allowable bending stress of 10 megapascals and an allowable shear stress of 775 kilopascals. Determine the maximum intensity W of the distributed loading that it can safely support. Also determine the maximum safe nail spacing for each third of the length of the beam. Each nail can resist a shear force of 200 newtons. So first, let's determine the safe intensity W based on the allowable bending stress and based on the allowable shear stress. By symmetry and by experience, excuse me, the maximum shear force is simply the reaction at the supports, which is WL over 2, and the maximum bending moment occurs at the center, which is WL squared over 8. So first, let's compute for Vmax, which is, if we base it to shear, WL over 2, the reaction here, or here, and Mmax is WL squared over 8. Now, the moment of inertia of the section is moment of inertia of big rectangle minus moment of inertia of the hollow rectangle. For the big rectangle, 150 plus 2 times 30, the base is 210, the height is 250. And for the inner rectangle, this hollow rectangle here, 150 by 250 minus 2 times 30, 190. So moment of inertia with respect to the neutral axis is 100, 210, 250 cube over 12 minus 150, 190 cube over 12. And that is equal to 187.7 times 10 to the 6 mm to the 4th. Then for Q1, this inner rectangle here, about the neutral axis, it is 150 times 30, then its distance is half of 250, 125 minus half of 30, 15, so 110. So Q1 is 150 times 30 times 110, and that is equal to 495,000 mm cube. For the maximum Q, so we add further the contribution of the side section, half of the side section, which is 2 times 30 by 125, and half of 125 is 62.5. So it is equal to Qmax for 95,000 plus 2 times 30 times 125 times 62.5, the contribution of this side sections, half of side sections. So it is equal to 963,750 mm cube. So based on shear, allowable shear stress is 0.775 megapascals equals W, assuming W is in newtons per meter. Length is 6 divided by 2, so that's in newtons. Then VQQ is equal to Qmax 963. So WL over 2, 963,750 over moment of inertia. V is equal to 60. 60, the sum of this shear, critical shear section, because if uh, critical shear section, which is 60, 30 plus 30, the section crossed by the neutral axis is 60 mm. The total is 60. And that is solving for W. W is 3019 newtons per meter. Based on bending stress, 10 WL square over 8. So 10 is WL 6 square over 8. That would be in Newton meter if W is in newtons per meter. So we multiply further by 1000 to convert it to newtons mm. Then C is half of 250, 125 over I, 187.7 times 10 to the 6. So W L square over 8 times 1000 times C, 125 over I. Solving for W, W is 337 newtons per meter. So the maximum or the safe intensity of the load W is 3019, the lower value, newtons per meter. Then for the spacing, S, so we have to compute shear force for the section 0 to 2, and is by symmetry, it's the same maximum shear in this case from 4 to 6. So same that section and that section. The maximum shear force is simply the reaction, which is WL over 2, so 9057 newtons. Substitute into the formula S equals Ri over Y, where Y or area Y is equal to 150 times 30 times 110, this expression here. So S should be less than equal to R, which is 2 times 200 newtons. There are 2 nails. Then quantity I, 187.7 times 10 to the 6 over shear force for that section 0 to 2 and 4 to 6, 9057. Then the Q of area, which is this area here, which is Q1, 495,000. So S should be less than 16.75 mm. Then for the second part, when or for the section from 2 to 4, the maximum shear there is equal to this shear force 9057, then minus W times 2. So P between 2 to 4 is 9057 shear force here, then minus area W times 2 meters. W times 2 meters. So it is 3019 newtons. So substitute into the same formula. We replace this shear to 3019, the rest the same. So 2 times 200, what is 7.7 times 10 to the 6 over 3019 times Q, which is area Y, for 95,000. So S is less than 50.24 mm. So that's it for this video.